This is a quick algebra-based physics example of impulse momentum, a golf ball. This example is actually going to be a two-part example. Here's the first part. A golfer strikes a 45-gram golf ball with her club, resulting in the ball leaving the golf club with a speed of 80 meters per second. If the interaction between the golf club and the ball lasted 5.0 milliseconds, what was the average force that the club exerted on the ball? I've typed down some of the key words that I think of when I read this problem. I read it and I realize it's an impact problem. There's an interaction, an event. It's a before and after scenario. These are all cues that momentum is going to be a great tool for solving this problem. Specifically, this is definitely an impulse momentum problem. So let's remember what impulse momentum is. Impulse momentum, we have J, that's the impulse, is equal to the change in momentum, delta P. So whenever there's a before and after, we have to think about what we know about before and after. So first off, what's the event that separates before and after? Well, it's the actual impact of the golf club against the golf ball. So before the impact, the velocity of the golf ball is 0. It just sits there. After the impact, we're told that it heads out at 80 meters per second. Before, the golf ball has a mass of 45 grams. That's 0.045 kilograms. And you know what? That's the same after. The mass doesn't change at all. And we also know that the time that this whole thing lasts was 5 milliseconds. That's 0.005 seconds. So now it's time to dissect our equation a little bit. What does this equation turn into? We can expand it. So J, impulse, we can describe in terms of the average force times delta time. Now the question asked us to solve for average force, so great, we've got that in our equation. And we know delta time, so this is all looking pretty good. Delta P, what does that mean? Well, it's the momentum final minus the momentum initial. Momentum, just a reminder, is mass times velocity. So our initial momentum, that's 0, since the initial velocity is 0. Our final momentum, that's equal to the 0.045 kilograms times 80 meters per second. So the final momentum here, this actually looks kind of small. The final momentum is 3.6 kilograms meters per second. So let's package all this up a little bit more neatly. So here's our impulse momentum equation. Let's put the numbers where they belong. The average force, I don't know. I'm trying to figure that out. But the time was 0.005 seconds. And then the final momentum was 3.6 kilogram meters per second, and the initial momentum was 0, so we don't have to put that in there. So my average force is just going to be 3.6 kilogram meters per second divided by 0.005 seconds. Resulting in an average force of 720 newtons. So that is our answer to the first part of this problem. Let's take a look at the follow-up second part. All right, this is the same scenario, a 45-gram golf ball being struck with a club, leaving at 80 meters per second, but this time we're given a graph of force versus time. And the question is, what is the maximum force exerted on the ball by the club? Well, the way we solved this problem before is we reduced it to, instead of a maximum force, we considered an average force. So there's some average force that acts during this entire time. So this is an average over the time. And what impulse really is the area. And when you reduce the problem to an average force, then you're calculating the area here of a rectangle. So we can call that the height of the rectangle, which is the average force, times delta t, which is the width of the rectangle. Well, in this problem, we're shown the actual graph of the force, and forces usually don't have these straight lines. It's usually a little bit of a curve, but a triangle's an approximation. And now the maximum force is on the graph as at the very top here. So this very top is the maximum. And so it's still area that we're working with. And so instead of reducing the area to a rectangle approximation, we have this triangle that we're going to work with. We're going to calculate the area of that triangle, which is going to involve the maximum force. Let me show you. So I've sketched a quick copy of that graph. It's supposed to be a triangle. It looks a little wonky. And I've marked the maximum at the top, which we don't know what that is. That's what we're trying to solve. The base of the triangle, though, we know that that's 5 milliseconds. So once again, we are going to use this definition of impulse, that it's the area under the force versus time curve. So what's the area of a triangle? Well, we usually write it as 1/2 base times height. Sometimes students are a little bit confused if that applies to all triangles, and it turns out that it does. You can kind of prove it to yourself by breaking up any triangle into pieces and kind of putting it back together. So in this case, the base is going to be my 5 milliseconds, which was 0.005 seconds. The height in this case is F max. And so the total impulse is 1/2 F max times 0.005 seconds. And this whole thing, again, impulse is equal to the change in momentum, which we calculated before. And so we know that 1/2 times the maximum force times the time of the interaction, 0.005 seconds, should equal 3.6 kilogram meters per second, was what we found before. All right, so now we just have to do a little bit of algebra. So here's where we left off. Let's go ahead and simplify this just a little bit. So half of 0.005 is 0.0025. So this maximum force is going to be equal to 3.6 kilogram meters per second divided by 0.0025. You may have already realized that this is just going to give us twice our average force, but we can go ahead and calculate it with these numbers just to be sure, and the result is indeed 1,440 newtons. All right, and we've finished this example.